That should.
We went, Laura always wanted to go there, so I think we went there.
I think that's not
On the agenda, we have fun time.
I went to the.
Oh, the ones that- Opposite. Yeah, those are so good.
You mean just consignment? Because we do a lot.
All right, why don't we begin the afternoon session? I guess this is the first one, but also remote. So our first speaker is Madan Kui Hao, and presentation is on evaluating the impact of resolving hourly anthropogenic emissions on health simulations in the United States using that. Do you want to share the screen, or do you prefer we do it here?
I could try sharing it first, and if it does not work, could you please share the screen? I feel like.
Okay, yeah, we can do that. Why can we not share?
You have to do the share button and then the entire screen.
Yeah, that's what I do.
It worked for me already. Oh, yeah, there comes the.
Or I could try because.
Now it's working.
Okay, thanks.
Go ahead.
Okay, thank you. Hi everyone, my name is Madan Kui Tao. I am a PhD student at Columbia University. Thank you so much for allowing me to join remotely and right now helping me presenting this slide in person. Today I will talk about integrating hourly NEI emissions into the standard CEMS anthropogenic emissions over CONUS and its impact on the simulated concentrations of major air pollutants and their diurnal variations. Before I start, I would like to thank all my collaborators for their insights and support shaping this work. Can you click on next, please? This figure from the EPA report shows the trends of criteria air pollutants in the United States as percentage above or below the national ambient air quality standards from 1990 to 2022. We can see remarkable improvement in air quality over the last 3 decades. But if we zoom into the last 5 years, we do see some fluctuations or even worsening conditions that all highlight the ongoing need for research-informed regulations in the US. Looking at the next slides, please. I've heard the term georing brought up in recent discussions, referring to this network of instruments on board the geostationary satellites that are providing us or are expected to provide us with daylight hour monitoring of trace gases, such as formaldehyde and nitrogen dioxide. This network includes the GEMS instrument in operation right now, covering the Asian Pacific region, TEMPO over the North America, which we care about probably the most in this audience, which was launched last year and will provide us with publicly available data starting this April, and Sentinel-4, which oversees the Europe region and is scheduled to launch soon. With this capacity to detect all these diurnal variations from space, we're more motivated to think about the representation of diurnal information in the models. Click on next, please. The diurnal variations in the concentrations actually really reflect very complex interactions across various factors, as some of those ones I highlighted on this diagram. All those could influence the air pollution concentration that we care about at a specific location and time. For example, a rush hour traffic could lead to an episode of high air pollution from the human activity side. Next, please. In my prior research just submitted to JGR Atmospheres, I explored the site-specific features of diurnal variations in formaldehyde and nitrogen dioxide, focusing on this transect. Click on next, please. Maybe 3 times, sorry. Thanks. I focused on this transact spanning from Rutgers, highlighting green from upwind to New York City, to those three orange sites that are closer to the urban core of New York City, and the downwind side, including Westport, Flax Pond, and New Haven, which is highlighted in purple because it has a lot of local traffic emissions. Next, please. The key objectives of this study is to look at the spatial patterns in the diurnal cycles and the correlations between changes in the surface versus that in the column densities. Next, please. Just showing one figure from this study, this plot here compares the observed summer mean hourly concentrations of NO2 at each site, represented by a different colored line. We can see differences across sites in terms of the diurnal range and when the daily max or mean concentrations occurs. Click on next. Button, you see the orange line for Queens College and blue line for New York Botanic Garden that shows very similar features for those sites that I showed earlier in orange that are closer to the urban. And click on next. You will see this purple circle that highlights a third local maximum in New Haven. This is also seen in the carbon monoxide surface concentrations with really continuous high emissions from where the site is located on the intersection of several major highways. So whereas this research kind of explores observed diurnal variations and try to explain and associate that with site-specific features in emissions and meteorology. Next, please. Today, we're more going to focus on how perturbations in emissions inventory will affect the simulated concentrations in the models. The two key research objectives are how do the simulated trace gas concentrations as well as their diurnal variations will differ when we are using the standard CHEMS emissions compared if we're switching in the CONUS using the 2017 NEI emissions. And the second question looks at how the temporal resolution of this anthropogenic emissions will impact the concentrations and variations. We choose to focus summer of 2018 because there's a lot of air quality field campaigns that we could use to do the model evaluation. Next, please. We use the musical version 0 setup, which is basically this framework of CESM with the community atmosphere model with full chemistry on the ChemChem and the horizontal mesh refinement through the SE, which stands for the spectral element dynamic core. The unstructured grid I'm using has 14 kilometers over the CONUS and transitioning to the 1 degree global resolution. Next, please. This table shows the configuration and emissions input for the base case simulations. We run this from the start of January to the end of August 2018. And this setup is kind of pretty standard and used also in the publications with Musica version 0. Oh, next, please. Thanks. So besides this base case, we also run 3 sensitivity test simulations highlighted in, I think, beige or orange shown on the screen, with emissions perturbations, as well as examining the influence of switching to the TS2 chemical mechanism. And those two emissions perturbations have a 30% reduction in total anthropogenic emissions or total biogenic emissions. We also conducted 2 additional 1-month simulations in blue here, replacing the CHEMS with either hourly or monthly NEI emissions over the CONUS. Okay, next, please. Actually, unfortunately, all the model simulations and analysis were stored and run on the MIT file server, which experienced a crash on January the 3rd, practically since when I submitted this abstract. But today I will share a few figures and statistics that I saved locally to show some preliminary results. But hopefully I will be following up with all the analysis after we stored the data on the server. For model evaluation, I divide the corners into these 6 different regions delineated by different colored squares. Click on next, please. When we compare the surface measurements from the state and local air monitoring stations, SLAMs, the model tends to overestimate its surface NO2 over most regions except and underestimate over the mountain region. It generally overestimates surface ozone and underestimate carbon monoxide over all regions. And this is for the daily mean concentrations. And next, please. We also compare the troposphere vertical column densities after applying the averaging kernel from TropoMe product. And we find that compared to TropoMe, the model tends to underestimate column NO2 and overestimate column formaldehyde. Next, please. If we're looking at the perturbations, starting with this figure on the left that shows the difference in monthly NOx emissions between AEI and CHEMS, the prevalence of this blue color across the corners indicates that we generally have lower NOx emissions from AEI, but we could also see some red areas where the AEI shows higher emissions. Next, please. The figure here on the right contrasts the simulated NO2 concentrations using the hourly NEM emissions versus the base case. And not too surprisingly, with lower emissions overall from NEI, we also get lower surface NO2 concentrations. Next, please. The simulated surface ozone concentrations is also lower when we're using NEI, which actually brings us closer to the observation from SLAMs. Next, please. Just for sharing some preliminary takeaways, I apologize for some of the bullet points you didn't see figures, but overall we see some biases in the model's concentrations. And when we are replacing the emissions inventory using NEI, we see better agreement with observations in surface concentrations and column formaldehyde, but we also see increased model bias towards more the negative side, or like lower model bias side in the NO2 column. For the emissions inventory selection, it will tend to influence the simulated daily mean concentrations more than using a different temporal resolution of NEI. But for all those things, we see notable regional variability. Next, please. For the next step, we're going to examine the modeled diurnal profiles of different trace gases and explore the characteristic unique to specific local location setting. With that, next, please. I would like to wrap up my work. I'm happy to discuss any of this in more details, and thank you again for your attention.
Any questions?
So I saw the NO2 curve dependence on the local time. I'm surprised that some of them peak at like 4 in the morning. Is that really traffic or due to some other factors?
That's a really good question. So for the surface NO2 concentrations, the higher time actually occurs, the first daily maximum usually occurs before the sunrise, and that's because there's no photolysis at that time, and NO2 concentration tends to be influenced more by planetary boundary layer dynamics. And before sunrise, there's no photolysis happening, and there's a NOx titration often occurs in urban areas, and that is when usually we see the minimum in ozone concentrations.
Any other questions?
Well, thank you again, and we'll move on to the next talk, which will be given by Lu Wang, and it's the sectional cloud model for CESM2.
it's easier to use the.
Or you can-
So it's. I just said that she.
I have to use this.
No,
You can open it.
not sure if I'm loud enough. Hello, everyone. My name is Lu Wang. I'm a student at the CU, and my talk is sectional cloud model of CESM2. So basically, it's a cloud sectional cloud model versus the default CESM2 model, which is MG two-moment model. And the sectional model means for a certain hydrometeor, we describe it with very fine size bins instead of two-moment, just number, mass, concentration for one mode. So basically, our sectional model as liquid cloud, ice cloud, both in sectional, both described sectionally, and these arrows are just related physical processes. We ran this model for a whole year for 2008 and compare with annual run based on MG two-moment cloud model. Also, if possible, compare with data. And we compare the cloud optical properties and some other general properties one by one. First, start with optical properties. This is droplet effective radius. It's effective radius for cloud droplets. On the right side is overland. Left side over land, right side over ocean, and the color scheme will be the same. Also solid line for land, dashed line for ocean, and black line for our current model, and blue line for MG model, and red line is the MODIS. So basically, these two big panels are our model run result. As you can see, both overland and over ocean, MG looks comparing well with the annual MODIS observation, like overland peaks around 10 to 11 micron. Over ocean peaks about 12 to 13 micron. However, there's another literature which is this little panel down here. It's also MODIS data. It's 10 decadal average based on more recent MODIS data, like our observation, our model simulation actually fits this Stevens et al. Observation much better. Over land is around 12 micron, over ocean around 18 micron for effective radius. And here's the map, global map for the annual average. The top two are from our common model. Left one is the effective radius based on all particles less than 50 micron, which is similar to what MG did. And the top right panel is camera effective radius map based on all size range, because our size run up to raindrop size. And you can see, we can see simulate a lot drizzle and raindrops over there. And the bottom one left is the MG result. And the bottom right is Moody's. As you can see, we MG is kind of lack of relatively larger drops than our simulation. And this one is a brief comparison for cloud ice effective radius PDF. Black one is our model. MG is in blue. You can see like both models have a large size range for ice, but our ice peaks at relatively small size, and MG peaks at relatively large size. And this right one is a comparison from model and observation from another paper based on CESM1. So basically, this blue line is karma model simulation. It's based on CESM1, and our model is based on CESM2. This we can pick up this small peak here, but we are lack of this large peak here, which is more or less similar to the peak from MG model. And next optical property is cloud optical thickness. So the top left is the common model, top right is the MG model. You can see the patterns are similar, but we have a lot more higher optical depths for liquid, probably because we are covering the drizzle and the raindrop size. And this bottom panel here is just Moody's average, annual average from literature. You can see we are in general, our model simulation has a higher optical depths than Moody's. And this is optical thickness for cloud ice. Right one is the common model. Right one is the MG model. You can see MG model has higher ice optical depths, particularly overland, than common model. Next one is liquid water path. Top left is the common model. Top right is MG, and the bottom one is the Moody's annual observation. In general, I mean, just the peak area between 60 north and south. You can see in general, model has a lower liquid water pass than Modis. For our model, we get a little bit higher values for this property. And for cloud ice water pass, left one is the common model, right one is the MG model. The patterns are similar. MG model has a higher, have some hot spots for cloud ice water pass than us. And next one is cloud liquid water content. The top left is our model, top right is the MG model. The bottom one is some observation data based on CloudSat and Calypso observation. You can see these two models are similar. We are a little higher in liquid water content. Also, both models has higher liquid water content observation. And this one is the ice water content. Again, left our common model, right MG model compare with CloudSat and Calypso. You can see the general patterns, the observation and models matching, and we are a little better than the MG model. And next one is the cloud fraction profile for between two models. Left one is the common model, right one is the MG model. You can see like they are quite similar, only like some details, like for example, like this is the north south pole area. We have a little bit higher value, but it's kind of trivial. I also checked the precipitation, annual precipitation pattern between these two models, and they are kind of quite agree. And last I checked the top of atmosphere radiation from between these two models, also compare with observation data. The observation data are solid lines. They are from series, and MG model are the dashed lines, and our common model is asperious. The black one is long wave flux at top of atmosphere, and the red one is absorbed solar. So as you can see, our model still have quite a big discrepancy between observation, especially over the tropical area. We have a little bit too much POA radiation flux, and we are like right now we are investigating on it to see what caused this discrepancy. So basically, this is the summary for our sectional model for liquid droplets, we have expanded the size range to drizzle and raindrop. Also for ice, we expanded to snow. We don't do the arbitrary auto conversion, but solve coagulation equation, which has more physical meanings. And secondly, I got a feeling we have our liquid droplet simulated better because we do see large droplets, which is observed in nature, but not much in MG model. And our model simulation is comparable to MG simulation in terms of cloud water content, cloud fraction, and precipitation. And last is the too high top of atmosphere radiation flux, which we are investigating on it. So that's all. Thank you.
Are there any questions?
So you showed the several comparisons that seemed like you have much more maybe raindrops or other things in the tropics than for MG skiing. So was that still a shortcoming in the model? You're saying you're investigating the shortcomings in the tropics. So it looked like there were sometimes very different patterns in karma than in the observation.
So for example,
Yeah, if you go a few slides back. Yeah, like there.
this one.
That looks like, I don't know if this is the same scale, but if it is, it's very different, right? And especially on the tropics.
See, yeah, this is the optical depth part. So we have a little bit higher optical depth here. I think maybe because our size range also go up to large drops like drizzle or raindrop size.
And is that not the case for the observations? On the bottom? I mean, I assume it's the observation on the bottom.
Yeah, the observation is on the bottom. It's not a apple to apple comparison because it's a MODIS observation. And MODIS can only retrieve a droplet up to 30 micron. Larger than that, I mean, MODIS cannot see it.
Okay, so we shouldn't say that the bottom is something we should compare the top left to, but just, you think if this is more realistic, the karma, than the MG scheme?
That's the
But that's all.
best I can do, because we do include the raindrop size, but the MG doesn't.
Okay.
And when we think of light attenuation, we should consider about large droplets. That's my thought.
Any other questions? Yeah, thank you. Yeah.
Oh, thanks.
Oh, sorry.
Can I just ask
Yeah,
a naive
sorry.
question? Does karma and MG represent all the same microphysical processes, or are there major differences?
They cover similar topics, but the way they try to simulate the algorithm is different. For example, from cloud droplet to raindrop, and the MG algorithm do some auto conversion, like has some empirical equations have exponents there. There's no physical meaning there. Like you have to do tuning to make it even better. And for us, we cover the full range from cloud drop to raindrop. And when they grow from small to big, they follow the coagulation equation. So it's more time consuming, consume more computer time, but it bears more physical meaning there. It doesn't do arbitrary things for the same physical. Yeah.
How much more expensive is Karma?
So far, it's quite expensive. Like we are like 10 times slower at the least, but we are doing some tests and we can optimize for sure.
Thank you.
Yeah, no problem.
So then next speaker is Martina Bramberger, and her presentation is on implementing a parameterization of convective gravity waves due to the obstacle affecting TAM and WACM.
I think it's already downloaded on the bottom.
Go to the far right there.
Yeah. If you go on the bottom, yeah. Well, thank you for the introduction, Nick. I'm going to build on what Julio already presented yesterday. I'm going to talk about our implementation of the moving mountain mechanism into 10 vacuums. And we already showed some really exciting results yesterday. And I want to give a little bit more context today of how Joan and me came about the idea of implementing this mechanism into TAM and vacuum, and also want to show first results and talk about next steps. And before I start, I want to acknowledge all of my colleagues that are mentioned here who contributed to this work. Yeah, Julio already introduced it very nicely yesterday. The moving mountain mechanism basically describes waves that are stationary to the cloud, which is given here on the right-hand side by the sketch with the blue outline. And these clouds are generated, or these waves, I should say, are generated when there is shear at the top of the latent heating cell, and this convective cell is acting like an obstacle to the ambient flow. So you can think of it as truly acting like a mountain to the ambient atmosphere, but in our case, the mountain is moving, hence the name moving mountain mechanism. And we have evidence from numerical studies and from also observational studies that these waves have large amplitudes, so they will account for a comparatively large portion of the momentum flux. And in our work, we use the parameterization that is based off of work done by Jager Richter, published in 2004, Beres et al. 2004. And in that work, she described a parameterization based off of a linear model for waves that are emitted from a stationary heat source. And this parameterization uses a lookup table approach, where the lookup table is a function of the heating depth and the wind speed. And the original hope for this work was that we would improve the representation of the QBO, especially in the lower stratosphere, because these waves usually have low base speeds. And this hope was basically given by a study, Alexander et al. 2021, where we compared the parameterized momentum fluxes to observed momentum fluxes. And you can see it here on the left-hand side. We show the parameterized momentum fluxes simulated by vacuum.
And on the right-hand side, balloon observed momentum fluxes from the pre-Concordiasi campaign. And the orange circle highlights that especially the momentum fluxes that are larger than 100 millipascal are missing in vacuum. And then furthermore, when we take into account the momentum flux phase speed spectrum as it is given here on the further right side, if we compare the momentum flux phase speed spectrum as it is simulated in vacuum 6 given in red, the shape compared to the observations that are given in green is very realistic, but we are missing a large part of the momentum fluxes, especially in the phase speeds. And if you then initialize the various convective gravity wave scheme with TRIM observations, which is given here in purple, you see that then you get a momentum flux phase speed distribution where the momentum fluxes at the higher phase speeds become very realistic. And this is good news because this basically means that the Barry scheme as it is implemented right now in vacuum and in CAM is actually doing what it was designed to do, which is parameterizing momentum fluxes for high phase speeds. Another takeaway that I have from this plot is that actually what vacuum needs in order to have a realistic QBO is more momentum flux in the low phase speeds. And one way to include the momentum fluxes in the low phase speeds is the moving mountain mechanism. So in that study, Alexander et al. 2021, we then used the parameterization as it was given in Barris et al. 2004. But this time we only used the part that describes the stationary component, and we described the convective sources with TRIM and used error interim to describe the wind speeds at the top of the latent heating cell. And you can see that this way we introduced a significant amount of momentum fluxes at the low phase speeds up to 10 meters per second. They're very especially large amplitudes in the westward wave flux, which is you can see here, which might help to improve the easterly phase, but also these large amplitudes at the low phase speeds might help to with the descent of the QBO down into the lowermost stratosphere. So what this parameterization looks like right now is given here on the slide. I give a brief overview. The assumption is that the connective cells are moving in the direction and with the speed of the wind at 700 hectopascals. The input parameters are the latent heating depth, the wind at the top of the latent heating cell relative to the motion of the latent heating cell. This is important. And then we also take into account the peak heating strength. You can see that here the resulting momentum flux is proportional to the square of the peak of the latent heating. And also we assume that about 5% of the grid cell is covered with convection. Important differences to the existing Barry schemes are that really we are here moving in the frame of reference, moving with the convective cell. So the relative wind, the relevant wind that we need for this parameterization is in the frame of reference, moving with the convective cell, which is also true for the wind shear. Also, the wave propagation is in the opposite direction to the relevant cloud top wind, which is given here on the top. And the momentum flux is not a function of a spectrum of phase speeds, but it really is just a single phase speed. So for each phase speed, we have one momentum flux. I also want to highlight some differences to the moving mountain realization that Julio showed us yesterday. In the work that I'm presenting here, at the moment, we use the Schenck-McFarlane latent heatings as inputs. I'm not using CLUB at the moment. The steering level is set at 700 hectopascal, which shows you that we are targeting deep convection right now. And also the launch level is at the top of the latent heating, which is shown here for a case study that we did in order to make sure that the parameterization does what it's supposed to do. You can see here on the far left-hand side, different latent heating depths at or profiles at different time steps. And the middle shows the launch altitude relative to the latent heating profiles, and also then the resulting latent heating depths that we use to determine the momentum flux. And starting with my next slide, I'm going to show preliminary results. I need to highlight that the results that I'm going to show are from a run that only covered 4 years. The 10-year run, unfortunately, only finished Sunday evening, so I haven't gotten around to analyze this one yet. But here we go. Without any further ado, I want to start with the vertical distribution of the zonal drag in this case. And you can see that with this parameterization, we input basically drag from the troposphere up to the top of the model. This is an exciting news for me because I've worked the past year to get the drag above 100 hectopascal, which was mostly related to getting the wind directions right relative to the cell. But now you can see how we have like a really nice drag distribution also in the stratosphere. Then when you look at the latitudinal distribution, I show here on the left-hand side for 77 hectopascal and on the right-hand side for 50 hectopascal, you can see, and I should mention this is an average over the 4 years of simulations. And you can see that most of it is concentrated around the equator, but we have some momentum fluxes that are also going up to the mid-latitudes, and most of it seems to be focused also in the southern hemisphere. Then I also computed a first momentum flux phase speed distribution. And indeed, most of the momentum fluxes right now is focused at phase speeds of about 4 to 5 meters per second, which is exactly what we would expect. And which is also a parameter that I will use to tune this model. So what I haven't mentioned yet is that these runs are untuned. So basically where we are right now is we have finished a 10-year run. We still need to tune this parameterization. And in order to tune this parameterization, we are going to use Stratio 2 data, which are super pressure balloon observations around the equator at 2 different altitudes. One set of balloons was flying at 18 kilometers altitude, and another set of balloons was flying at about 20 kilometers altitudes. And from these balloon measurements, Milena Korkes, a postdoc at NWA, derived momentum fluxes. And I show here momentum flux phase speed distributions on the left-hand side for 18 kilometers, on the right-hand side for 20 kilometers. And this is what we will then use to validate the momentum flux that we get from the lookup table method for the moving mountain mechanism. And I also want to highlight one other, what I find a exciting result. Oh no. Let's see if this works. Yes. So if you take a look at the peaks, so here at 18 kilometers and here 20 kilometers, you can see that a lot of, almost half of the momentum of the waves have been filtered between 18 and 20 kilometers. So this is already an indication how important these low phase speed waves are in order to drive the QBO down to the lowermost stratosphere. So I said that. So we come to the conclusions. We have implemented now the moving mountain mechanism as an additional source for connected gravity waves. And the results that I just showed, we used a lookup table approach based on Barry's et al. 2004. And the drag was mostly distributed around the equator and the southern hemisphere. as well as in the upper troposphere and mid-stratosphere. We haven't done any tuning yet, but we will use the balloon measurements, as Julio also mentioned yesterday, to constrain these parameterizations. And our next steps are that we want to keep on analyzing the impact of these parameterizations on the QPU, but also more excitedly on the southern hemisphere stratospheric vortex. We will constrain the tuning with the measurements. We might also experiment with the input latent heating by combining Club and Cheng-McFarlane. We haven't done that yet. And also experiment with the steering wind level, which is at the moment set to 700 hectopascal, but maybe we want to extend this to more shallow convection, and that 700 hectopascal as a steering wind level doesn't make sense anymore. And with that, I thank you for your attention with a mountain wave picture from yesterday evening, basically.
Any questions?
Like you have a lot of negative drag in the trade wind regions. Do you expect to get a lot of drag there? I didn't think there was so much convection going on.
I didn't think either. That was a surprise for me to see that much drag in that area. And I have made these plots yesterday, so I haven't had time yet to look further into them. But I was surprised by it too.
Would that be accompanied by a change in the surface
Yeah.
wind stress?
Yeah.
Just to follow, that was my question too, but I'll ask
Yeah.
another one. So is it keying off momentum fluxes from Club, but doesn't have to be in any condensation region, is that right? Or-
No, so this one, what I just showed, is based off a lookup table approach.
Okay, sorry.
What Julio showed yesterday is keying off of the momentum flux from Club. So at the moment, they are two slightly different methods if you want to look at it that way.
Yeah, because it's a very slow waves, so in the summer, will they be like mountain waves? Will they be more filtered in the true pulse region?
I would expect so, yes.
Okay.
Yeah.
And the other thing is that, because, their surface would more prefer eastward wind, does that have any implications on the anisotropy of the waves, after passing through?
I think so, because the wave propagation is dependent on, like, it's opposite the direction of the wind in the convective cell. So if the convective cells have a preferred eastward propagation, it will definitely also impact the propagation direction of the waves. And that mechanism.
Yeah, I didn't, you plot the base velocity spectrum.
Yeah.
Is there asymmetry actually?
I didn't plot it here because what I plotted here was the absolute value.
Oh, okay.
So that's why all the phase speed was positive, but I will have to distinguish between the positive and the negative phase speeds, definitely. Yeah.
Thank you again. So I think the next speaker should be remote. So hopefully, I did not see the slides, so hopefully you're able to share your screen. Mohammed, you are here. Yeah, there we go. Okay, we can see your screen. We can't hear you. You're getting muted.
Well, can you hear me now?
Yes, we can hear you now.
Yeah, that's it.
So his presentation is on investigating the impact of uncertainties in methane emissions and halogen chemistry on methane abundance and lifetime. So please go ahead.
Thank you. My name is Amin Mirzai. I'm a PhD student at the University of Arizona, working in Dr. Abarano Research Group. Today, I want to discuss about my research project about the impact of methane emission, halogen chemistry, and methane abundance in lifetime simulation. And this project, I'm working with Dr. Ben Gubert, and I want to thanks to other co-authors for their help. So first, I provide a background and motivation for the work. Nowadays, we see a lot of studies about methane. It is a reactive greenhouse gas, but still, although we have a lot of observation and measurement from satellites and Chrome-based, still estimating methane flux is have high uncertainty, and also we can see in commonly in most of the chemistry climate models, they consider prescribed methane instead of actual methane emissions. So using prescribed methane could have benefit. Maybe we can have more consistency in different simulation, but it can also buffers atmospheric consolidation effect on methane. So there should be need for a emission-driven simulation for methane to capture methane's interaction with tropospheric oxidants like OH. But still, there are very few studies that use methane emission in chemistry climate models. The next uncertainty would be in short-lived halogen representation in chemistry climate models. They can affect the oxidative capacity of the troposphere by modifying ozone and hydroxy radical concentration. And if we consider two main paths for methane oxidation, that you can see, one way is the reaction with the chlorine, and the other one reaction with hydroxy radical. But most of the oxidation happens with the reaction with the hydroxy radical. When we apply reactive very short-lived halogen in the in the chemistry part, so we could expect that we actually destroy ozone in the troposphere because of actually very low ozone precursors like NO2, and this reduction destroying ozone will also reduce the hydroxy radical, because the main source of OH is ozone. So by reduction in as you can see, if we have less ozone, less hydroxy radical, actually we would have less methane loss. Then when we have less methane loss, we would have more lifetime for methane in the atmosphere. And also maybe we can see in the continental part, as you can see in the right figure, it is captured from the Nature Communication paper. When we have the prescribed simulation, mostly it's most of the methane loss happens in tropics and near surface. But when we apply halogen chemistry, we can see a reduction in OH and consequently reduction in methane loss, especially in open seas. And in the continent, maybe because we can have VOC limited or NOx limited regime in highly polluted region. So in this, for example, in VOC limited regime, if we reduce NOx, we can actually improve ozone production. So based on these two backgrounds, we want to consider methane emission in the simulation, and also using short-lived halogen representation in the simulation. So we would have 7 simulation in CESM version 2.2 CAMCAM. The first simulation, TS1 is representative of reference case. It is the default chemistry with prescribed methane from CBIP6. And for anthropogenic CO, we use CAMS, and for fire, we use spin version 2.5. Then we have two more simulation without changing the chemistry, but just using GCP Global Carbon Project emission, two set of emission from surface inversion and Gaussian inversion. And the fourth simulation is used by changing the chemistry by adding very shortly collagen representation in the CAM, but still prescribed without emission. Then two more simulation with the emission, but now we have a very shortly collagen chemistry there. And the last simulation, which is the seventh one, the last one is the combination of a very shortly halogen chemistry, methane emission, and also having better CO emission from Moffitt inversion. This is how the GCP Global Carbon Project methane emission distributed globally. In the left panel, you see the mean of Gaussian and surface inversion for methane. In the right panel, we see the changes, the difference between Gaussian and surface emissions. You can see the main difference between China, Middle East, and Africa, and South America. So looking at the simulation, in the top panel, you see methane total column, CO, middle CO total column, and ozone tropospheric column. We start the simulation from 2014 until 2009, beginning of 2019. We used 2 years for spin-off until 2016. Then we compare the result from 2016 to 2018 with the ATOM big campaign and also index site. From this figure, as you can see the evolution of the methane, how it changes if we don't consider halogen chemistry and just using emissions. You can see the values diverges compared to prescribed, maybe because of high OH available there. But when we use halogen chemistry, we're more close to the prescribed, and it reduces the drop in methane. See how it's shifted. Then using also when we use CO posteriors from Moffitt, it's also improve the methane estimation. The same thing we can see for the methane, and also we see the drop in ozone tropospheric column. Here is the difference between different simulation compared to the reference case, which is the default chemistry with the prescribed. As you can see in these first two simulation on the left, only applying emission, we can see a significant decrease in methane. You can see this is the zonal mean average, different latitude over time in different months. We averaged from 2016, entire 2016 to 2018 for each month, and show it the zonal mean for different latitude. As you can see, the methane decreases about 80 ppb, but for the CO and ozone tropospheric column, the changes is not significant. But when we apply the halogen chemistry without emissions, you can see we have to see increase in methane. This is small because it is prescribed. But for CO and ozone, you see CO increases and ozone also decreases, and you can see when you see the decreases in ozone and also increases in CO. Then when we use emission-driven simulation with halogen chemistry, then the difference between the with reference case, still we have a reduction in methane, but compared to the simulation without halogen chemistry, we see that the drop is reduced from 80 ppb to about 30 ppb, and it also shows sensitivity to the changes in emissions. And also using CO version from MOPID also improve methane because it more reduced the drop in the methane. Of course, it also improves the CO. Then here's we have a comparison with the ATOM peak campaigns. ATOM one in 2016 July August, ATOM 2 2017 January to February, 2007 ATOM 3 2017 September to October, and ATOM 4 2018 from April to May. Also, we compare with index site for methane CO for the ATOM. We can compare with methane CO, and also here is the result of comparison with the ATOM. As you can see, the solid black line is the ATOM measurement. The orange dashed line is the prescribed simulation, I mean the reference case. With the halogen chemistry, not using the emissions, it doesn't change. It's overlap with the simulation because for the prescribed, we don't see changes in methane. But when we have emission-driven simulation, as we see before, methane decrease a lot. As you can see, this two dashed line is the emission-driven simulation without halogen chemistry. But this three solid line, mean red, purple, and cyan blue solid line are related to the emission-driven simulation with halogen chemistry. So there should be a shift for them, and this is a sharp shift. You can see how it's shifted to it reduces the bias compared to the ATOM measurement. And this is also happening in different seasons because, as you can see, ATOM happen in different seasons, and this is consistent in all the seasons. The same things we can see for the CO, but the variation is smaller compared to methane. But we can see that if you consider prescribed, here you can see that using halogen chemistry also improves CO. For the ozone, we also show significant improvement in ozone. As you can see, this line is the prescribed, and also the without halogen chemistry. And when we apply halogen chemistry, it's we reduce the bias, and it's more close to the ATOM measure. Here is the summary of the what I've shown for the ATOM. As I mentioned before, we can see that the bias decreases from minus 90 to about minus 30 to 40. This is for emission-driven without halogen chemistry. This is emission-driven with halogen chemistry. For CO, also the same thing. We can see the same thing, and for the ozone, also we see improvement. Then comparing with the index side in the North Hemisphere, you can see in the left panel the comparison with the methane for the methane, and the right panel is the comparison for the CO. The first plot is for the green line. The green dot is for reference comparison of index site with the reference case. When we are applying emissions, you can see the error and correlation changes. Error increases and correlation decreases. But with applying halogen chemistry in purple, with emissions, it reduces the error and also improves the correlation. As I also we saw before, we use CO posteriors is also improved the simulation. The same as for the CO, we can see in CESM 2.2 improve methane, CO, and ozone and background atmosphere, and also using CO posteriors also improve methane. We can also see that emission-driven methane simulation improves yield, and uh, using very short-lived halogen chemistry in CSM 2.2, we could have more reasonable emission-driven simulation. And using emission-driven methane simulation, we can have more choice for check the sensitivity of the chemistry in the model. Yeah, that's it. Thank you.
Thank you. Are there any questions? Yeah, Susan, do you have a question, or this is what you have in the chat?
Oh, what I have in the chat, please. Thank you.
Okay, I can read it. So this is a question from Susan. Do the methane lower boundary conditions have heterogeneous structure similar to emission sources, or are they spatially average values? And also, are the lower boundary conditions determined from ground-based emission inventories and or satellite observations, or a combination?
I think for the lower boundary, it's based on the CMIP simulations. But for now, we use the GCP, which are based on the model inversion from surface and GOSAT. Yeah.
Doug, you have a question?
So do you think going forward for assessments, we should use emission boundary condition and for methane? Just apply it that way?
Actually, with emission-driven simulation, we could have more realistic simulation. So, and also we can also check the interaction with the chemistry. So I think we need for the future to have these both together, No
other questions. So thank you again.
Mm.
Last time before we have a break, will be given by Zheng Zhu and investigating the runaway of CSM under extreme warm conditions.
Thank you. Hello, everyone. Thank you for being here in person and virtually. I'm Jiang Zhu from the Paleoclimate Group at NSF NCAR. Today, I will present my research on investigating the runaway of CESM2 under extreme warm conditions. So what do I mean by model runaway? Let's look at some results from the early Eocene simulation using CSM 2.1. In case you don't know, early Eocene was a very warm hothouse climate, occurred roughly 50 million years ago, and the CO2 is estimated to be 5 to 6 times the industrial level, of course, with a large uncertainty range. And on the left, we have the global mean surface temperature time series simulation with different levels of atmospheric CO2 concentration. On the right, we have top of atmosphere net radiation against global mean surface temperature. So this is a Gregory-like plot. And you can see for simulations with lower CO2, perhaps up to 3 times the pre-industrial level, we have stable global mean surface temperature, and the top of atmosphere radiation decreases with a global mean surface temperature and approaching 0, suggesting that we will have equilibrium simulation converging solution. However, for higher simulations, simulations with higher CO2, for example, the 4 times CO2 in red, you see that the global mean temperature just keep increasing in the simulation. And look at the top of atmosphere net radiation. It firstly decreases with global warming. That's a nice sign. for converging, but for further warming, the rate of decrease weakens, and they even start to increase with the global warming, meaning that we won't have a converging solution. The model is blowing up. So that's what I mean by model runaway. And you can see from previous slides that we may need to run coupled simulation for multiple hundreds of years in order to show this runaway behavior. So next, I'm going to simplify this problem using pre-industrial based slab ocean simulation to reproduce this problem. So everything is pre-industrial except CO2 level. And similarly, you see that for lower CO2 up to 8 times the pre-industrial level, we have stable simulation. For CO2 higher than that, the top of atmosphere radiation start to increase with warming. And compared to the coupled Eosin simulation, I think one thing it becomes clear is that looks like if we have a threshold, it's not in the CO2 concentration, it's more likely in the surface temperature. So looking carefully here, you can see that after the global mean temperature approaches some value maybe around 35 degrees C, the top of atmosphere radiation start to perhaps increase with the warming, so leading to this model crash. And you may wonder what's the previous CESM model version of model doing. And in the middle, we have CESM 1, CAM 5, and you can see that the model show similar this runaway behavior for CO2 level up to 16 times the pre-industrial level. And for CESM 4 with CAN 4 physics, the model is very stable, simulates very stable warm temperatures in this simulation with 128 times pre-industrial CO2. And at the end of the simulation, the top of atmosphere radiation is 0. So we have very nice converging solution. You may wonder that is this a real problem? So should we expect runaway in reality at this temperature range? I think that the runaway is unrealistic based on a couple lines of evidence. The first is that higher temperatures have been simulated in cloud resolving model with line-by-line radiation. Basically, more accurate models can simulate this warm temperature. Secondly, the Earth was stable in its recent past. For example, if you look at the Paleocene-Eocene thermal maximum occurred 50 million years ago, the temperature was estimated to be 34 degrees C, and the CO2 was about 7 to 8 times the pre-industrial level. So based on that, we think this is unrealistic. And for us, from the paleoclimate perspective, we want to use CESM2 for hot climate research. And we think that it's reasonable to aim at a stable global mean surface temperature of around 40 degrees C. And there are possible reasons for this model runaway in CESM2, could be due to cloud processes or clear sky processes. And we can try to address this. So again, the slab ocean simulation and the top of atmosphere radiation. The first thing I'm going to show you is we can decompose the net radiation into clear sky and the cloud radiative effects. So you can see that focusing on the clear sky part, you can see that initially the clear sky net radiation decreases with warming. However, after some temperature, maybe at about 35 degrees C, the top clear sky radiation start to even increase with warming. So this suggests that there are likely problems in the clear sky processes. And we can further decompose the clear sky component into long wave and short wave. And you can see that in the long wave, after some temperature threshold, the top of atmosphere, a long wave OLR stopped increasing with warming. Basically, CESM2 is not effective at cooling itself at this temperature range, so leading to this model runaway. Given that this is likely a clear sky problem, the first processes we investigated was radiation. So basically the radiation RTMG that was used in both CESM1 and CESM2. And this is also partly motivated by a series of papers published recently, suggesting that the lookup table in RTMG is too narrow. So the gray band here is the lookup table for RTMG. During model runtime, if your air temperature fall within the lookup table range, then you are good. You will have pre-computed gas absorption coefficient. However, during model time, if your temperature fall outside this lookup table, you end up with inaccurate gas absorption coefficient. In Clough et al. 2021, this paper, they carefully showed that looking at the long wave only, they find that the RTMG gives us unrealistic ECS bump over warm temperatures when you compare that with line-by-line more accurate calculation. And this temperature range has relevance for our early use simulation. And I want to reinforce the point brought up yesterday by Brian Medeiros that we really need a more accurate radiation in CESM3. So here, again, the gray is the lookup table in RTMG, and the red now is the instantaneous time temperature from CESM2 simulation. So I have 1 year of simulation data. And you see that even for the pre-industrial, looking at the stratosphere, we already have some values that fall outside the lookup table. And we also have seen that in the code and at the simulation. This could occur over the Antarctic. And moving to the warm future climate change 4 times CO2 simulation, you see that we have maybe even more a problem over the stratosphere. And looking at the lower troposphere, we're starting to break the upper bound of the lookup table. And luckily that we have this new radiation, RTE plus RTMGP, and it has much wider lookup table and is more accurate. So next, I'm going to reproduce the work done by Clough et al. I use idealized temperature profiles and specific humidity, and I benchmark the radiation scheme against the line-by-line calculation. So the line-by-line is black, and you see that the new radiation in blue is indeed more accurate. So basically, you remove this unrealistic bump in the RTMG. Now, with a better radiation, does that solve our runaway problem? Unfortunately, no. So the model still runs away. Looking at the right column, you can see that the only difference between the 2 sets of simulation is one use RTMG, one use the newer, better radiation. And this is ongoing simulation, but you can already see that for this warm temperatures, a warm high CO2, we still have this runaway behavior, and the temperature threshold maybe is still around 35 also. And this helps us rule out like large biases in the radiation. Then we can focus on cloud and convection related parameterizations. And I have done quite a few investigations, and the simulation that is very interesting is that when you start with CESM2 Chem 6, you turn off the cloud, use the older UW set of schemes, you can have more stable simulation. So the stable temperature can be above 40 degrees C, and the top of atmosphere radiation decreases with warming. This is suggesting we can have a stable hot climate simulation. And given also that this is likely a clear sky problem, that motivated me to further simplify the problem and focus on the water vapor. So here I'm showing profiles in temperature, net radiative heating, water vapor, and relative humidity in pre-industrial based fixed SST atmosphere only simulation. So I have different degrees of uniform warming from 4K all the way to 28. And then before diving into also the dashed lines means Chem 6, solid lines means results from Chem 6 with cloud turned off. And before diving into the detail, I want to point out a couple key features of hot house climate. The first one is that different from relatively cold climate, we'll have very warm SST. We expect radiative heating over the lower troposphere. And this is associated with the closing of water vapor radiative window, and it's supported by robust physics. And the second feature is high water vapor and a strong vertical gradient. And this is again supported by simple thermodynamics. So the exponential dependence of water vapor on temperature. So these key features may have implication on how club is doing in simulating the hothouse climate. And let's look at the results. First, the dashed line is the club simulation here with 28 uniform SST warming. And you see that we even have a relative humidity above 100%, a pretty steady water vapor over the entire column. This is unphysical. And the second feature, if you look at the orange here, you can see that for even colder temperatures, clouds tend to simulate a higher relative humidity. And I think this means that stronger water vapor feedback if we run the simulation in fully coupled setup. And I won't go into detail about this slide, but basically saying that if I do some parameter tuning, they do not improve the simulation. And this is a summary. CESM2 runs away when global mean temperature reaches 35 degrees C. And this is likely a cloud problem, not directly related to radiation or clouds. And the cloud simulates higher water vapor in the upper troposphere and a large warming. And water vapor is a greenhouse gas. And when we run cloud in coupled simulation, this can amplify the surface warming, eventually leading to the model crash. And I want to point out that this may have implication for present day climate and abrupt 4 times CO2 simulation. Recalling the instantaneous temperatures I showed you, in the abrupt 4 times CO2 simulation, the surface temperature could reach 320 K at instantaneous frequency. And the club tuning with C6 or C7 seems not helpful. And this indicates that this may be a structural problem. Perhaps the empirical based PDF need to be revised for hothouse climate. And again, I want to stress these key features of the hothouse climate that may be difficult to parameterize in CESM. And that's it. Thank you for your attention, and I look forward to any suggestion you may have. Thank you.
Any questions? I will ask one. So based on what you present here, it seemed like the same problem would be in CSM3. That's likely true.
CSM3 use a new version of club. I haven't got a chance to test that.
Okay.
So I don't know. Okay.
So club and microphysics are very tightly coupled. Can you rule out that that's not playing a role here?
Yeah. One thing I want to point out is that the previous investigation focusing on the ice age climate found that microphysics is very important in setting the model sensitivity. Here for greenhouse climate, mixed phase processes, they do not matter anymore because it's very warm. But the other microphysical processes may be important. But I have other simulations with you change the microphysics version. And in the end, I think it's more likely to be a problem in cloud instead.
So when you run CSM2, is this, in chem, just normal, I mean, just the normal physics, you don't couple to like secondary organic aerosol changes. You just use whatever there was, right? That could be another factor, because if you have a much warmer climate, you probably get more biogenic emissions that will produce more aerosols. So that coupling isn't included. But that will be somewhat included in our new model version, where we do couple with the Megan emissions. So that may be another thing. And other things like fires are all prescribed, right? And so there are some aerosol interactions. Do you think they matter?
I don't know, it could be important. But what I'm showing here in
Yeah.
this plot is fixed SST pre-industrial, everything pre-industrial. But if you have like any idea about what should I tell, I'm happy to do that. And thank you.
Adam, you have a question?
I had a suggestion because that's what Jiang, you asked for some suggestions. There's a so the way that we do the saturation adjustment in we do it in club, and we do it after we've converted our cam variables to theta L and total water, which are club's variables. And so we do the saturation adjustment in the theta L total water space. And then we eventually convert those back to temperature and humidity. And I found that that conversion back doesn't necessarily maintain the saturation adjustment. And sometimes you do see things like 101% saturation in our model. And so there is a hard fixer in the CAM interface to club. It's just a nameless that actually does a hard saturation adjustment after you've converted the variables. And so it would just be easy to rule out that there isn't some problem at high temperatures with that sort of conversion and how we're doing the saturation adjustment. So that would be my suggestion, just to rule that out. I could email you the name list.
Okay, thank you. Good to know.
You showed a lot of global mean plots. Is the problem traceable to a certain region of the globe that starts? Is it like the tropics where it's already the warmest?
Yeah, I think that's a good question. And I haven't figured out a good way to identify where the problem first show up. I think if our like the physical processes starts from warming, starts from long wave radiation, maybe it's the tropics. That's part of the reason I'm focusing on the tropics in this type of cloud. But I think I would like to do some single column simulation if I can learn how to do that. That would be another way to try to address your question.
So there's no more questions. So thank all the speakers in this session. So now we have break. We're going to come back at 2:45. What time to do? 2:50?
2:55, then we're 10 minutes late.
Okay. We'll restart at 2:55.
Are you ready? Sure. Okay. So, thanks for those who still here after the break. We want to start with Danny, and we need to share. I'll let you introduce your talk. And I will try maybe to stick to the 15 minutes. That means about 12 plus 3 minutes, if that's okay. We'll see how we do. No pressure.
I'll try my best.
Okay.
Yeah, hi, good day. I'm a postdoc, ASP postdoc here. So today I'm going to talk about deriving a historical dust emission data set to evaluate aerosol radiative forcings. So just talk about mechanistic dust emission scheme this morning, and more specifically for air quality modeling purpose. But here I'm looking from a climate perspective, really talking about long time scale simulations of climate and its associated aerosol impacts on climate. And so again, I want to acknowledge my collaborators and mentors, Yatka Cook at UCLA, Lomeli and Nate Mahomo at Cornell, and also my anchor mentors and collaborators, Dave and Simona Timmers and Eric Kruzek. So thanks for being here. And here we go. Okay, so the point we are trying to make here is that current modeled aerosol mechanistic dust emission schemes, like for dust and for other aerosols, are calibrated towards present day observations. And so they, it's questionable whether they can be extrapolated to past and future climates. But that's what modelers are doing right now, right? In like most of the inter-model comparison projects in CMIP runs, for example. And so we are showing here that you see most of the ESM simulations in CMIP 6 could not replicate the historical increase in dust for the past 150 years since 1850s. This trend, this black line here shows the historical dust increase of about 50% from 1850s to year 2000. This is inferred from, or constrained from multiple sedimentary records of dust deposition fluxes across the globe. And there's no trend in the CMIP6 models. And so there could be ramifications in terms of aerosol forcing or climate simulation. So a few ones here, for example, models underestimate historical aerosol radiative forcings. For example, missing dust cooling, historical dust radiative forcing, which could potentially partially offset the historical warmings in the Earth system models. And so we are arguing that models need these aerosol radiative forcings to better evaluate the climate sensitivity. The historical increase in dust was likely due to, human activities, land use, land cover change, and climate change. We currently don't know how to model these interactions between these parties. So we're trying to parameterize it statistically or mechanistically. But for now, we have two proposed approaches to, sort of force model dust to follow the observed historical variability from, invert from the sedimentary records. First of all, we suggest using the observed historical constraint to tune dust. So you see this interdecadal variability in historical dust change here. For example, set 2000's dust to a global mean of 0.03 following the global constraint of the contemporary dust following David Ridley and Colette Hill. And then you set this global mean to 0.03, and then you trace this back, and you derive a decadally varying dust emission tuning factor back to 1850s. So that's how you constrain dust globally following the observed records. And the second one, that's what we are talking about in this talk right now. It's trying to constrain dust regionally and we are forcing a global dust emission data sets to fit those sedimentary records. So we're doing a little bit of optimization here. So let's focus on the derivation and some preliminary evaluation in the CSM2. So basically the method, just the main concept here, we have some dust deposition records across the globe here. We're showing the site locations of the sedimentary records, and we are showing the decadal time series of these dust deposition time series from multiple sources here from the past papers. So the goal is you see these rectangular regions here. That's the defined dust emission sources that we want to constrain in magnitude. So the goal is to optimize regional total emissions. We call that lambda here. For all the 9 defined source regions here, the 9 rectangular regions here, using the 19 dust deposition data sets for 19 different locations. So hopefully this is sort of an over-constrained problem. So quickly, the schematic. So this is following a very basic inverse modeling concept. We are using an ensemble of multiple model simulations of the relation between the dust deposition at a certain site or grid to the regional simulation of dust emissions in the I region. So there are 9 regions in total, 19 deposition time series in total. We have this 19 by 9 Jacobian matrix capturing the sensitivity, a linear sensitivity from multiple models. So hopefully an ensemble is better than one single model. We have the observations from the sedimentary records of dust deposition flux. We can, sort of design this cost function, a chi-square error, such that we can, try to force the 9 values of lambda to match best against those observations of dust depositions. And then we can do this decade by decade. We can obtain 9 values per decade and then redo it for all the decades. So we can obtain regional total emissions lambda for all regions as decadal time series. So now we have the 9, total regional total dust emissions as 9 values across the globe. What we are doing for the rest of the analysis is just to borrow the regional dust emission map from, back from these ESM ensembles for the present day climate, for the contemporary climate. We, take away its magnitude. We just, so if we normalize it to unity and then we just force or scale these regional emission maps back using the lambdas as decadal time series. So we are scaling these emission maps regionally up and down, summing them back up together. So we are forming this DustCon, what we call the DustCon version 1 emission data set. So this is a really simple inversion concept. We're just doing regional optimization. So there's no sub-regional optimization. So we hope we can achieve higher resolution inversion in the future DustCon versions. So just quickly introducing the, some of the specs of the dust emission products. It has a 2-degree horizontal resolution. That's the resolution of the ESM ensemble. It covers from 1841 to 2000. It has interdecadal variability, so it changes every 10 years, forced by the sedimentary records. So since it's forced by the observations, the global total emission increased by 50% across the 1850 to 2000. And again, each defined region has their own interdecadal variability. So you'll see, for example, the Middle East here has a larger increase historically than its neighboring regions, such as over Asia and the Sahara, for example. And then again, the subregional spatial variability of the emissions remains the same because it's just borrowed by the same ESM ensemble. And then a little bit about model configurations here. Again, we are using an F-HIS concept, transient land atmosphere coupled. CTSM with SPMO, CAM6 with MEM4 modal aerosol model, and an FV dicol in 22 CSM. What's the major difference here is we're using, doing a historical simulation across the century. So from 1851 to year 2000 with a time step of 13 minutes. So it's quite a long one. So here, a little bit of evaluation. So we're showing CTSM5 emissions from the land. It's basically identical to the dust column emissions because it's just reading in from the dust column emissions. You see this 50% increase in historical dust emissions. And then we're showing Chem6 dust AOD here. Again, we're showing this 50% dust increase historically from the 1850s to the 1990s. We are also showing the interdecadal variability in the CTSM5. So you see this interdecadal variability, the value changes every 10 years, which is the same as the dust column products, but you see some interannual variability from Chem6 because Chem6 atmosphere is changing historically year by year, or even day by day. So here we are just going back to that global plot, but here we're showing the red line as the CSM2 using dust column emissions. As shown here, the red line, you see it really captures the interdecadal variability of the dust reconstruction, the global constraint, and then as opposed to, for example, the blue line using CSM2 using a mechanistic dust emission scheme, namely Learn 2023, it's not really super coupled to the historical land use line cover change, for example. And again, it's flat, just like other CESM models shown here. So this is just a preliminary showcase that CSM using dust column, a prescribed emission product can generate this or reproduce this interdecadal variability of historical dust. Quickly showing some deposition evaluations here. We're just picking some sites, not all of them, some of them, showing that, again, the red line captures the interdecadal variability much better than other CESM models. You see the variability the magnitude is a little bit underestimated, but in general, it captures the variability. It does not, capture the deposition time series variability well, probably because of representation error. First of all, we have a grid level CSM dust deposition versus a site level sedimentary core dust deposition flux. And second of all, we probably have weakened emission variability during the optimization because variability across different sites could partially offset each other. So we have probably a little compromised variability. Finally, this is the direct radiative effects and forcing. Again, I'm showing 1850s, the first row, 1990s, the second row, and then subtract the two in the third row. So you see that in the CSM2 using dust column, we are regenerating, or we're generating this change in the dust cooling across the globe. It's increasing following the historical here. So you see strong historical increase in dust corresponding to the stronger dust cooling in the historical climates. And then you see if we're using a mechanistic scheme, we generate a really small direct radiative forcing of dust, and its sign is not, consistent with what we are doing in the dust column. So to put this into context, so we just show a negative, a dust cooling radiative forcing of -0.1. So to put it into context, the direct radiative forcing for all aerosols sum up it's 0.45. So this is from a recent 2020 study. So you see thus it's contributing to maybe 20 to 25% of the total direct radiative forcing of all aerosols. And this is important to incorporate into climate models to do a more realistic aerosol radiative forcing and climate sensitivity. So just a quick summary here, we're working on a PR to make this dust column data set available in CTSM. And again, if we are using mechanistic emission schemes, we suggest following the global dust constraint to globally constrain the historical aerosol radiated forcings. And lastly, aerosol modelers are currently using this DustCom dataset to evaluate historical dust radiated forcings in AeroCom phase 3 that's ongoing. So we have different participants from NASA, GITS, NOR, ESM, and other institutes. And then this data set is also going into CIMIT 7, so AirChem Mid 2 and AirHis Mid. That's currently initiated by Jasper Cook and Natalie McCall. So it's currently undergoing. So that's it. Thank you very much. I'll take questions.
Questions? I just have a quick question. We always tune our model to AUD of 0.03 or something.
Yeah.
But if we had that increase, we really for pre-industrial should tune it to 0.022.
Yeah.
It seems like.
Yeah.
So we'll really have too much forcing in pre-industrial in general, and then we don't get the track.
Yeah. Right.
That's pretty good.
Yeah. So 0.03 is
Good to know.
for 2000. Yeah.
Great. Thank you. We'll just move on, and if anybody has a question, we can ask it in the meanwhile. This is we do had a discussion to consider that maybe for a simulation, even for CEMIT, to somehow integrate this type of dust scheme, the prescribed dust scheme, in the model, if we can come up with some good solution how to do that.
Thank you.
Yeah, will be great. Thank. Next speaker is Longley online. Are you on the video?
Yeah, hi, it's Mang. Hi, everybody.
Do you want to try share your screen? Should I stop sharing my screen?
Oh, yes.
No, I
Please.
don't do anything. You can share your screen. Try.
Yeah, I'm trying. This is the first time for me to use this as I'm trying to find out how to share my screen here.
If not, I think this is the right.
Oh,
present.
yes. Yeah,
I can
great.
share, and you can just tell me how to yeah, I think that was the wrong one.
Thank you. Thank you very much.
Okay, yeah, I just tell me when to advance, and then I do that.
Okay, thanks.
Okay.
Thank you. Hello, everybody. Thanks for coming. I'm Longley from Cornell, working with Natalie Mahawal. Before getting started, I would like to thank my advisor for her continuous support and training provided to me during the past years. I also want to extend my thanks to all our collaborators for their contribution to this work. That said, in this presentation, I will talk about an effort we have been making to improve data modeling in CESM. Specifically, we have been trying to fix a well-recognized error source for dust climatic effect estimation by developing a new melting framework. Next slide, please. That is CESM2, working with MEM4, similar to many other climate models, substantially represents dust particles larger than about 5 micrometers in diameter. The model's size settings result in a near complete oversight of dust particles larger than 10 micrometers. For a long period, researchers paid few attention to dust particles larger than 10 micrometers because this fraction of dust was thought to be removed from the atmosphere quickly by a gravitational certain velocity because of their larger size. So they were thought to be not important for dust aerosol's climatic effects. Next slide, please. However, a series of recent combined measurements undertaken with in-situ and remote sensing instruments downwind of North America, finding that light dust particles, especially for those greater than 10 micrometer, contribute more than expected to the total dust mass. This measurement suggests that a substantial amount of dust aerosol larger than 10 micrometer and up to 40 micrometer are frequently present in the downwind region, so as far as 2,000 kilometers away from North Africa. Next, please. This fraction of dust particles larger than 10 micrometer not only contributes substantially to total dust mass, but also can contribute up to about 40% to the total dust extinction at the event, and that's the optical depth. This means that they could be more important than we thought before for the dust radiation interaction as well. Next, please. In fact, a recent study suggests a warming effect of around 0.03 watt per minute square by dust particles between 10 and 20 micrometer. And this warming effect occurs because cold dust particles also absorb a considerable amount of solar radiation compared to the dominant scattering effect by fine-sized dust particles. The second reason is that the short lifetime of cold dust particles confines these particles over bright deserts, which reduce the cooling effect of scattering and enhance the warming effect of solar absorption. In addition to warming effects, due to dust radiation interaction, recent studies found that dust particles with the size ranging between 10 and 20 micrometer can contribute more than 30% to the total dust deposition over ocean areas downwind of the source regions. Therefore, including this fraction of dust particles could change the estimated ion intrusions available for oceanic ecosystem from dust aerosol and the relative importance of ion sources between dust and humidifier, for example. So it is important to also include dust particles larger than 10 micrometer in climate models, which is the focus of our study. Next, please. We accounted for this fraction of dust particles by developing a new MEM10 code within dust species in CESM2 Chem6 model framework based on previous work in Chem5 with bulk dust. In our new MEM10 code, we tanned the dust particle size to up to 70 micrometer. In addition to this, we also integrate the other recent advance on dust emission physics into our new MEM10 code. I will not introduce those advances and relevant results here in this presentation, but just mention its existence as important revision to the model to understand the results I will present later on. Based on the special optical properties of very large dust particles, relative fine size dust particles, we also carefully designed a method to tune the amount of the newly added dust particles. I will not detail the method here as well. So please reach out if you have interest in it. Next slide, please. The model performance is assessed using a wide set of observations drawn from the literature covering diverse aspects of dust aerosols. This includes the standard data dust models often utilized, such as the AeroNet, dust optical depth, surface concentrations, and deposition flux rates. It also includes those that have not widely utilized yet, such as the relative effect, efficiency, size distribution, and particular mass of dust. Again, I will not detail all this here because of the time limit. Next, please. With a more advanced model, we provide a new estimate of dust body and the climatic impacts of dust, highlighting the importance of the climatic impacts by dust particles that has been previously omitted in the model. Next, please. It has previously been observed that cold dust particles settle too quickly in many climate models, including CESM2 Chem6. Our simulation using the untuned dust settling velocity confirms this finding, as indicated by the orange dashed line, which simulates dust up to 20 micrometer. So we tune the settling velocity of dust aerosol only in the new MEM10 code, such that the model size distribution matches better with the aircraft measurements than the untuned simulation does. But it still tends to overestimate the fine size dust mass smaller than about 2 micrometer and underestimate the dust mass between 5 and 20 micrometer. Next, please. Comparison between modeled and observed surface dust concentrations suggests a fairly well performance on capturing the observed spatial variation and magnitude within a factor of 10. We have also compared the model dust optical depths in the visible band centered at 0.53 micrometer with AeroNet and the model-based retrievals at the 0.55 micrometer wavelengths. The new MEM10 reproduced both retrievals fairly well, but it tends to overestimate the dust deposition flux rate compared to the data we have, largely because of the lower size cutoff in the observations. Next, please. The model still have has difficulty in accurately reproducing the satellite-based retrievals of dust direct effect efficiency under clear sky conditions. There's actually no significant change to the shortwave efficiency between MEM10 and MEM4. In comparison, the change in the longwave efficiency is more considerable. However, this change tends to increase the bias in magnitude if we consider the best estimate of the retrievals. So the model still can well reproduce a spatial variation. If we further consider the large uncertainty in modeling both the long wave, direct effect, and the optical depths due to many factors, including the large uncertainty in both the real and imaginary part of the complex reflecting index, we cannot tell with confidence whether the difference between MEM10 and MEM4 are statistically significant or not. The metrics were also derived from a limited number of model data pairs. Next, please. We have modified the code, enabling online calculations of three-dimensional political matter for dust errors only. This slide compares the modeled vertical profile of the particular mass across different size ranges with corresponding observations. Solid line denote observation and dashed lines model results. We found that the new model simulated the mass concentration more than 5 times higher than observations for fine size just smaller than about 2.5 micrometer. In contrary, it is simulated much lower mass concentrations for that between 10 and 2.5 micrometer. We didn't show results for from MEM4 in this figure, but both MEM10 and MEM4 simulate inadequate vertical transport of dust across all the size ranges, considering corresponding models. Next, please. The different size settings substantially change the relative importance of different modes for different dust quantities, such as the total dust optical depths in the visible band. As shown in this slide, in MEM4, about 89% of dust mass is distributed into the single cosmos ranging between 1.0 and 10 micrometer. It translates to about 62% contribution from the single cosmos to the total optical depths. This number could be even higher near dust source regions. Therefore, it is the single cosmos that solely determines the total dust optical depths. This means that when tuning the model according to optical depths, one needs to tune the dust mass distributed into the single cosmos. Next, please. It is not the case in the new MEM10 model. With the current size settings, the accumulation dust cosmos contributes over 3 times higher than it is in MEM4. This accumulation dust mode is even more important than the second dust mode on global average. Over major dust source regions, they are more comparable than over the other areas. The two dust modes contribute about 96% of the total optical depths on global average. So when tuning the model according to optical depths, one needs to tune the dust mass distributed into the first two modes in MEM10. In contrary, these two modes contribute only about 10% of the global dust deposition, which is proportionally less compared to their 96% contribution to the total optical depths. Next, please. In this schematic, we summarize and compare the simulated global dust quantities obtained using MEM4 and MEM10. The total dust optical depth in the visible band is insensitive to dust particles larger than 10 micrometer. So even though both models have global total optical depths comparable with each other, the total global dust emission is much higher in MEM10 than in MEM4. This is because primarily of including dust particles larger than 10 micrometer. The dust loading or boarding, however, is comparable between the two models, because majority of dust particles larger than 10 micrometer gets removed from the endosphere due to their short lifetime. MEM10 simulates a strong cooling with the net effect of negative 0.26 watt per meter square. This stronger cooling effect is because MEM10 simulates more fine size dust particle than in MEM4, though the newly added dust particle less than 10 micrometer tends to warm the planet. The cooling effect is simulated for both shortwave and longwave spectral ranges. Next, please. To end this presentation, key takeaways from our preliminary results include that we have successfully integrated recent dust model developments developments into the dust model within CSM 2.6, particularly focusing on addressing the missing fraction of dust particles larger than 10 micrometer. This integration has led to the creation of a new model, MEM10. In this MEM10, there's a stronger dust cooling because of the competition between the fine size dust and the particles larger than 10 micrometer. And finally, the introduction of the new model, which has constraints on coarse and giant particles, has resulted in a fair reproduction of certain observations, such as the surface concentration within order of magnitude. However, it has not fully reproduced all observations well, particularly the vertical profile of the mass concentrations. This highlights the need for additional refinement and improvements in the model. And this take-home message underscores the importance of ongoing research efforts to improve our understanding and the representation of dust erosion in climate models. And that's it. Thank you very much.
Thank you. Very nice. Thank you very much. Are there questions? I think well, people think about questions, and we'll already have Jane come up for the next talk.
Thank you.
Thanks so much for the presentation, and we'll move on to and this is your talk. Yeah.
Hello everyone, this is Chen Zhang. Today I'm going to talk about effective radiative forcing of stratospheric wildfire smoke simulated by CESM MEM3. My postdoc supervisor is Brian Chung at Stillwater, and my previous PhD supervisors are Shawnee and Pompey. I'm now at Stillwater Labs, and the job here we plan to couple the common cloud and common aerosol modes in CSM model, and we are working with CMO. And thanks to CMO, we now have a version that was on CSM2. We have common aerosol modes. We are still working on common cloud developments, which Lu has a talk this afternoon. Hopefully, this work will help better represent aerosol cloud interactions in climate models. But it could take years or more. We didn't know how long it could take. So let's get back to the talk today. First, I'd like to introduce RCB. To simplify, we can say RCB is a special kind of extremely wildfire-induced deep convection clouds. Here we have a deep convection here, so the smoke particles can be injected into the stratosphere through the deep convection in the RCB clouds, and the energy can be penetrate the tropopause. So previous studies have shown that the RCB smoke injected into the stratosphere is comparable to small to moderate volcanic surface aerosols. Recently, we have two record-breaking RCB events. We call 2017 P1E event and the 2019 to 2020 Australian New Year event. And we have a figure here for the stratospheric aerosols, which shows the injected mass into the stratosphere. And the vertical axis shows different events, include volcanic eruptions and RCB. For example, we have small to moderate volcanic eruptions here, which injected about 0.4 to 0.5 telegram surface aerosols into the stratosphere. One record-breaking RCB called the 2070 Pacific Northwest event, which injected about 0.3 telegram small particles into the stratosphere. Most recently, another RCB called the Australian New Year event, evaluation, we call it NY, which injected 3 times that of previous record-breaking LCB event here. So it injected about 0.9 or 1 telegram small particles to the stratosphere. So here, however, the radioactive forcing of LCB smoke has not been considered in climate assessment reports. For example, we have observations from satellites which shows a global warming with a radioactive forcing values at the PUA of 0.53 watt per square meter, which include greenhouse gases and aerosols for all-sky radiative forcing at the TUA. We also have model simulations for volcanic surface aerosols, which shows a cooling effect from volcanic surface aerosols with a value of minus 0.08 watt per square meter. So our science question here is how much does the PyroCP smoke contribute to global radiative forcing? So we use the CESM MAP3 model to simulate these 2 record-breaking PyroCP events. We would like to quantify the smoke radiative forcing, and we also would like to compare that to volcanoes. So we have 3 sets of ensemble experiments to simulate both PyroCP smoke and volcanic survey. And each set contains 6 member ensembles, so it could be time consuming. For each set, we have a control experiment which has no PyroCP smoke or volcanic survey. And for the PyroCP, we injected the smoke particles into the tropopause at about 12 kilometers. So, and we also have the 3rd experiment for volcano eruptions, which injected surface aerosols, but we injected with the same aerosol mass to the experiment 2 here. So we want to make a apple-to-apple comparison to PyroCP smoke. So we validated our model simulations with satellite observations. We compared smoke SLD and found it generally consistent with satellite observations. For the figures here, we have PNE event on the left and NY event on the right. So we have a time series of SLD. So we find that for PNE, we got an increase of 1 time background SLD within the first 1 or 2 months, and it decreased to background in about 9 months later. But for NY event, it increased about 4 times that of the value of background SLD and decreased to a background in 1 year later. So we also simulated a strong stratospheric warming for the NY event, which also agree with data. This figure shows that for the vertical profiles of stratospheric warming for these 2 events. For the NY event, we find that the stratospheric warming is located at about from 12 kilometers to 23 kilometers. And we also find that most importantly, the stratospheric warming was located at about 18 kilometers, which agrees with the smoke. Because the smoke is mostly located at 18 kilometers based on observations in our models. So we have a global stratospheric warming above 1 centigrade for about 4 to 6 months, and it persists for more than 1 year over 0.4 centigrade. The observation of the stratospheric warming here is due to the observation of solar radiation by smoke particles, include black carbon and some absorbing organics. Also, the smoke particles warm the stratosphere, but it can cause us effectively. So we have simulated the radiative forcing from TUA to 200 HP and at the surface. What we like to highlight here is that due to the stratospheric warming, the warmed stratosphere can emit a long wave adjustment in both directions. One branch back to the space, which can close down the Earth at the TUA more effectively. So if we compare that to volcanic surface aerosols without a significant stratospheric warming, which has no significant long wave adjustment back into the space, we can tell the volcanic surface aerosols cools down the Earth at TUA with a value of 0.1 watt per square meter. But for stratospheric wildfire smoke with long wave adjustment, we got a value of minus 0.17 watt per square meter. So we can say the smoke particles generate 70% more negative values at the TUA. Mostly it's due to the long wave adjustment here. And if we look at the surface, due to the observations of sunlight at the stratosphere, less sunlight could reach down to the surface. So we got more negative values at the surface for parasitic smoke with a value of minus 0.37 watt per square meters, which is 270% more negative values than volcanic surface. So to conclude, the snowman like the parasitic smoke more because it goes down the Earth. But for the volcanic surface, the head of the snowman could be melted due to global warming. Here we also have another work shows the radiative forcing values at the TUA, but here we injected small particles and volcanic surface aerosols with the same XLD. In previous studies, we just showed that for the same mass. So we notice here there are some differences between the optical properties for small particles and surface aerosols. So in here we can exclude the impacts of different optical properties. So we have a figure here for the correlation of effective radiative forcing at the TUA with SAOD. So for the red color here, we got a value of minus 23.5 watt per square meter per SAOD for volcanic surface aerosols. But for parasitic smoke, which is colored in black, we got a value of minus 37 watt per square meter per SAOD. So combine these two works together, we would like to highlight the long wave adjustment and their importance in the radiative forcing at the TUA for parasitic smoke, which is also often ignored in previous studies. So here's a conclusion here. We got we simulated the annual mean effective radiative forcing for the NY event at the TUA 200 H-bar and at the surface. We also highlighted the long wave adjustment from the warmed stratosphere is pretty important and is often ignored in previous studies. And we further compare that to mass equivalent volcanic surface aerosols, and we find that the parasitic smoke could close down the Earth more effectively with a value of 70% to 270%. Here's publications related to this talk. Thank you for your listening.
I have a quick question. Oh, okay. So parasitic events like this one is usually not included in our models, right? You artificially included the smoke because usually we don't get the smoke all the way in the stratosphere.
Correct? Yeah, the default model doesn't contain the parasitic smoke at the stratosphere. So
yeah, so that means in the time series we are missing those forcings really.
Yeah.
Yeah, and the
yeah.
heating and everything.
Yeah.
Just to clarify. Thank you.
So when you inject the same amount of sulfate and the black carbon, so what about the particle lifetime? Does the black carbon have similar particle lifetime in the stratosphere as sulfate, or it stays longer or it stays shorter?
That's a good question here. We have some figures for small particles with sulfate aerosols. We also have a line plot, solid line plot, but it's not showing this slide. Sorry about that. We can, from our simulations here, we can say due to the self-lifting of small particles, because each warmed the surrounding atmosphere and it could rise to the higher altitude. So our simulations here could tell, maybe shows that the lifetime of smoke could be slightly longer. But I believe we still need some observations to validate this. And so it's just model simulations.
Yeah, it looks like the bottom is the sulfate, right? Declining faster than.
Yeah, the bottom one is for sulfate and the top one is for smoke. And the sulfate aerosols just goes down due to the gravity.
Yeah, right.
So maybe it's one possible reasons why simulations like this.
Thank you.
There's a question and online, and from Susan. Did you also transport gases with the aerosols into the stratosphere? Like, is water vapor one of the gases if you transported it?
That's a good question, we didn't see this value. We didn't see this output.
But did you inject only the aerosols, or did you also inject water vapor?
We only injected the smoke, the aerosols. So we didn't take a look at the water vapor.
Yeah, and the second question is if has there been studies of the impacts of the extreme wildfires from the last summer, 2023, on the stratosphere?
We haven't done that. So
Not yet.
Not yet.
Okay, great. One more question.
Yeah, quick question. So in the two-panel plot where you show a comparison between model and SAGE, it seems like in the 2017, there's a very gradual increase in the model, which doesn't really capture the observation, but in the later one, it really captures the rapid increase very well. What's the difference between them?
We are not 100% sure about this, but we for previous period here, we just run the model for spin up. So the first 1 or 2 months could be not so good, but so it could be related to the model experiments, but I'm not 100% sure.
Okay. Great, let's move on to the next talk. And I have 2 more talks, and this will be both on nitrates, so it will be interesting. Of course. Thank you.
Hello, everyone. Today I'm going to talk about the nitrate aerosol simulation for the Asian tropopause aerosol layer called ATOL. My name is Yun Chen, and I want to thank all my co-authors for their contribution. So the Asian tropopause aerosol layer formed during the Asian summer monsoon season near the tropopause. The left panel shows that the updraft from topography updraft during the Asian summer monsoon, and it will bring up those pollutant and the precursors for the aerosols up to the upper troposphere, and then form this atoll inside the anticyclone. marked by the blue. And those aerosols can also be is mainly stays in the anticyclone, but it can also transport up and to the outside to other regions. The composition of atoll is under investigations. Not until recent campaigns, including the ECLIP that involved the INCAR colleagues, that we start to understand more about the composition of atoll. The right side is the recent paper by Hoffner et al. Showing the ammonia nitrate observations actually happening back in 1997, is one of the most important contributors to the to the atoll. And this is also one of the things that I am working on in this talk. So I would like to briefly introduce the model development history that our models CSM1 Karma is starting by Pengfei Yu in 2015, who putting the tropospheric aerosols, including sea salt, dust, organic carbon, black carbon sulfate, and with a bulk SOA scheme. And in 2022, Pengfei and I we worked on adding the nitrate into this model. So the model has two more elements. One is nitrate and one is ammonia. And so for that study, the surface to 300 millibar, we use a mosaic to form the nitrate. And above that level, higher altitude, we use the ligand phosphidase to form the liquid nitrate ammonia containing particles. And this, we find this scheme is not sufficient enough to simulating the atoll, which is a very localized aerosol layer. So this work, I modified the nitrate formation for the pressure level lower than 300 millibar using the Clegg's thermodynamic model called EAIM, to estimate the formation of solid ammonia nitrate and the solid ammonia sulfate. And I'm also including the law in the Hansen to form the liquid nitrate particles, which is the same process that forming the polar stratosphere clouds in the stratosphere. I also reduced the mixed particle radius to 1 nanometer in order to better represent the growth process of the nitrate aerosol, which was missing before. And also we allow more ammonia transport to the UTLS region following one et al. 2022, which find about 10% of the ammonia actually transported to the upper troposphere. And this model run also include the volcanic injections to better represent the stratospheric aerosols, and other parts are the same as at all in 2022. So here I just give a brief summary of what is included for the ammonia nitrate and ammonia sulfate. So for the temperature that's warm, above 198 degree, the ammonia is preferred to form ammonia sulfate, which is in form of the lithosite, and then the rest ammonia will form the ammonia nitrate. When the temperature is between 198 and 195 at the UTLS condition, ammonia sulfate will actually deliquescence, and which release the ammonia to form the ammonia nitrate solid. And when the temperature is lower, and both ammonia nitrate and ammonia sulfate are in the liquid phase, and which the curve of the nitrate growth is actually very similar to the STS polar stratospheric clouds. So we validate the model using 3 field campaigns and MePass satellite. This one shows the 3 campaign location in the south, middle, and the north branch of the Asian summer monsoon. First, I'm looking at the aerosol composition and compare with the stratocline Erica observation, and we find that organics, nitrate, and sulfate are the major contributors of atoll in our simulations. We are very happy to see it is actually within 2 times difference between the model simulation and the observation. Especially, we are very well represent the increasing line of the sulfate here. So another instrument that measure the composition is the MePass. They use a spectrum retrieval to retrieve ammonium nitrate. And this figure is showing the top panel is the MePass and the modeled solid phase ammonium nitrate, and the bottom panel is a gas phase ammonia. And we find the most ammonia is in the form of ammonium nitrate because of the cold temperature there. The model and the simulation and the observation are in the same order of magnitude, which means our model is actually transporting the reasonable amount of ammonia to the upper troposphere. If we look at the nitrate formation, we actually find nitrate is more than what observed, which is because the simulated nitrate is forming due to many 2 different reasons. So if you look at the yellow line circled area, that's where the ammonium nitrate forms with high nitrate concentrations. And then there's another peak is when the temperature is lower than 195 degree. And so the nitrate is actually peak at 100 millibar due to different reasons. So this figure is showing the composition contributions from different aerosols. And here, as we talked before, sulfate, organic, and nitrate and ammonia are contributing, have visible contributings to the atoll around 15 kilometer. And you can see the others in gray here. I'm plotting it, but it's invisible, which means the primary aerosols is transported to the UTLS from the surface is very, very minor in the model simulation. So, besides the composition, I'm also looking at other properties such as size distribution, and I will go slightly quicker here because we can see the model is doing a really good job, except in the 19 kilometers, we're missing a little bit of large particles. And also, this is one of the key observations we compare with to tune our model. And you can see that the mixed particle, which is a nitrate containing particles in the model, is fitting the size distribution of the black lines really well. It is because we add the nitrate growth to reproduce the size distribution. So that's the key figure of the model tuning here. And also the last comparison is compare with the GOMOD campaign particle mixing ratio, and we find we have the similar mixing ratio compared to the observation, but the observation seems to have a various atoll in the 3 days they launched the balloon, but the model doesn't change the altitude that much. And this figure is also important because this launch is in the north branch of the Asian summer monsoon, which has a relatively high temperature, and it's hard to form the particle there also. And by adding the ammonium nitrate is a key to reproduce this figure. So the last part is to, and I'm looking at some chemical impact of adding the nitrate aerosol in the model. The top figure, left panel, top left here shows the surface area density of the atoll is actually increased by 100% because of adding the nitrate aerosols formation. And adding the nitrate aerosols is causing the chlorine change by more than 150%, and the chlorine COO change is more than 150%. Chlorine nitrate is about 100%. HCl is decreased more than 20%, but the ozone change is quite minor. It's about less than 5%. So here's my conclusion. The nitrate aerosol in the stratosphere mainly consists of ammonia nitrate formed locally by ammonia neutralization and because of the condensation at cold temperature. For the Asian summer monsoon region, the nitrate, organic, and sulfate are the three major contributors, while other primary aerosols are very minor, including the nitrate in the model double the surface area density in the UTLS in the Asian summer monsoon region and a change in the chlorine partitioning in this region.
Thank you. Thank you. Other questions?
So the ozone change is relatively small, you said 5%, but what's the trend? Do you have any idea over time? Is a lot of this anthropogenic emissions coming up, or is it natural?
Yeah, this 5% is averaged in July and August, which should be the peak time of the loss, but it doesn't. And I'm guessing, I'm not a chemist, but I'm guessing it's the dynamic lifetime is kind of short, and also it's just generally very low there. So the ozone, it doesn't get to the, and the temperature, like the part that has the ozone change is where the temperature is low. And when it moved to the north, even we have some aerosol there, but it doesn't do much because the temperature is relatively high.
Yeah, we saw the same thing in the Salmonella paper for sulfate, where you get the processed chlorine that comes down and hits those cold temperatures. So it's interesting to see it in the nitrate too.
Yeah, I read that paper several times. So like here, I'm just including like what if we add a little more nitrate, what does it do?
Yeah. Very interesting.
We have a question online. Susan, do you want to unmute?
Sure, I can do that. Thank you, Queen. That's very interesting. I guess I'm not quite sure how you did the kinetics on this. When you have ammonia in these particles, you certainly change the acidity.
Right.
How did you handle that? I mean, that I would think would affect some of the reaction rates. Do you need to worry about that?
Yeah, so in the current model, we just assume everything is like the sulfate, like when the particle is there and it just go like the sulfate and the STS, it changed the surface area in the Mozart, and it doesn't consider the composition. So maybe that's one thing I should look into to see if actually change the.
Yeah, I think it would definitely affect the solubility of, say, HCl in these particles because they are presumably a lot more neutral than the pure sulfate, which are highly acidic. We can talk about it sometime if you want.
Okay,
But nice work. Nice work.
Thank you.
Thank you. Any other questions? If not, we go to our last talk, which is online. Wei Wang, you there?
Yeah. Yeah.
And I guess we figured out that it's easier if we share here, so I just do that now. Okay.
Oh.
So please let me
Okay.
know if you want me to advance the slides. Thank you.
Okay. Oh, hello everyone. Today I'm going to show some preliminary results of modeling nitrate aerosols over East Asia using variable resolution CSM2 coupled with mosaic. So next slide, please. So nitrate aerosols are expected to be more important in the future because their precursor emissions are expected to increase and sulfate aerosols decrease in wet regions. Also, the condensation of nitric acid on aerosols may contribute to enhanced aerosol activation to cloud droplets, and therefore may affect the calculation of aerosol indirect forcing. So even so, only a handful of global climate models consider the formation and the life cycle of nitrate aerosols in the atmosphere. This figure shows the simulated aerosol optical depths compared against aeronet observations over different regions. So in East Asia, the negative values indicate that models tend to underestimate aerosol optical depths. This may be related to underestimation of anthropogenic emissions over Eastern China and the lack of nitrate aerosols in the models. Next slide, please. Also, the model resolution also plays an important role by affecting aerosol emission, transport, and aerosol cloud interactions. So with regional mesh refinement, higher resolution global climate models have been developed. So in this study, we aim to evaluate model performance in simulating nitrate aerosols over East Asia using variable resolution CSM2 coupled with mosaic. So this figure on the right shows the variable resolution grids used in this study. So the resolution increased from 1 degree to 0.125 degree over East Asia. The atmospheric component is CAM6 with chemistry, and the aerosol module is MAM4, and coupled with the mosaic to simulate gas aerosol partitioning of nitrate. The model is free run for 4 years to simulate the present day climatology with the average of last 3 year results analyzed. So, in East Asia, the complex topography is captured by the high resolution via CESM. And in this figure, the red rectangle represents Eastern China with complex topography features such as Sichuan Basin and Taihang Mountain over the northern China. And the intense human activities produce significant anthropogenic emissions of aerosols and precursor gases over eastern China, which are associated with the formation of nitrate. So in this study, we will focus on the aerosol simulations over eastern China. This panel shows the emissions of two precursor gases in the simulations. So the spatial distributions of SO2 and the NOx are very inhomogeneous. And due to high resolution, the model can simulate points like high emission values over northern China and the Sichuan Basin. And the model can capture large gradients in emissions over small areas. So next slide, please. And then we analyze the regional budget of nitrate aerosols over eastern China. The formation of nitrate aerosols in our study include
the gas aerosol exchange loss and production, and the aqueous chemistry production, which is related to uptake of nitric acid to droplets. The main chemical reactions involve ammonium nitrate and heterogeneous reactions on dust and sea salt aerosols, which can occur in both fine and coarse modes. The results show that the loss from gas aerosol exchange is very strong and larger than the aqueous chemistry production. Over Eastern China, the nitrate aerosols are removed from the atmosphere by dry and wet deposition and transport across boundaries. Next slide, please. We then compare the simulated nitrate aerosol concentrations with the observations from the literature. So the results suggest that the model tends to underestimate nitrate aerosol concentrations at the surface over China. Next slide. Yeah. And this figure shows the variation of shows the seasonal variation of nitrate aerosols. The black line and the blue line represent the observations from China atmosphere watch night observations and the simulated results respectively. So the model can capture the seasonal variation of nitrate aerosols with high values in winter, which is related to active production at cold temperature. This panel shows the column integrated concentrations from simulation, and the top panel shows the burden of precursor gas, including the nitric acid and SO2. And the bottom panel shows the burden of nitrate and sulfate aerosols. So over Eastern China, nitrate and sulfate burden are consistent with the anthropogenic precursor gases, while over remote regions, dust and heterogeneous reactions play an important role. In addition, the complex chemistry and the short lifetime of nitrate aerosols can lead to large gradients in concentrations in small areas, which can be represented within high resolution via CESM. To explore the possible reason of underestimation of nitrate aerosols in the model, we further examine the burden of nitrate and the dust in fine and coarse mode. And we compare the results from previous studies, which are shown on the red panel. So compared to the results from Wu et al., which used E3SM at 1 degree, the model used in our study tends to underestimate the nitrate burden in fine mode, while overestimates the burden of nitrate and the dust in coarse mode. Next slide, please. So this indicates that the contribution of fine mode to nitrate burden is lower compared to previous study. So as resolution increased, the uncertainties in dust simulation may affect heterogeneous reactions of nitrate aerosols and therefore may contribute to the low biases in nitrate aerosol concentrations. So finally, we compare the simulated aerosol optical depth from models with different chemical packages. And we compare the results from with the satellite observations. And the red rectangle represents Eastern China, and the area averaged AOD values are shown. So compared to CAM-CAM, which improves the simulations of secondary organic aerosols, The default model CAM6 simulates higher AOD values, which are closer to the observations. The reason is that the CAM6 overestimates organic aerosols concentration over Eastern China and therefore overestimate the AOD over Northern China. When the nitrate aerosols are considered in the model, the CAM-CAM coupled with Mosaic can capture the high values over Northern and Central China, indicating an improvement in AOD simulations. Next slide, please.
Oh, something worked. Oh, there we go.
Oh, yeah. Yeah, so in conclusion, the performance of variable resolution CSM2 coupled with Mosaic in simulating nitrate aerosols over East Asia is evaluated, and the preliminary results are shown. The model tends to underestimate nitrate aerosols concentrations, which may be related to uncertainties in emissions such as NOx and SO2, and also may be related to uncertainties in chemistry parameter revisions such as heterogeneous reactions. And the low biases in aerosol optical depths over northern and central China are reduced when nitrate aerosols are included. However, the VRCSM2 needs to be further tuned to reduce uncertainties in simulation, such as dust emission. So that's all. Thank you.
Okay, thanks for the interesting talk. Are there questions? Yep.
How are you going to pin down the likely source of the error between the parameterizations and the emissions? I think that's the next question, isn't it? If you've got low concentrations, you said it could be one or other, or one and the other. How do we break it down?
Yeah, can you repeat the question slowly?
Sorry, yes. You talked about the low concentrations of the nitrate, and you suggested it was either the parameterizations or the emissions. How do you begin to decide which?
Oh, how to decide which? Oh, okay. I think the uncertainties in emissions may be lower than that in chemical parameterizations. But I think we can scale the emissions and change the chemical parameterizations in the future work. But I guess the chemical parameterizations may play a more important role.
Okay, does that answer the question? I have a question. Did you say you run a few years, right? How expensive was the simulation with Mosaic?
Yeah, yes. I don't remember the exact the time. Is I run this on Sharon. Yeah, I can check the record.
Yeah, it's
If
okay. We
you,
can follow up later. I just was curious.
yeah, it's I remember that it's very expensive. Yeah.
Okay. Any other questions on this? Nitrate is the version that we do have available from Doosan Yo, right? It's a branch of CSM2, but we don't have that available yet in the development version. That's the one you were using, is that correct?
Uh,
This is CSM 2.2, what you're using, correct?
yeah, CSM2, yeah.
Yeah.
Oh, the version is not has not been released. It's on released on GitHub.
Yeah. Okay.
Yeah.
Thank you. Okay. So let's thank every speaker again for the opportunity. The end, and that's great. We will resume tomorrow morning in 2 different places. The atmospheric group will meet here, and the webcam and CAD/CAM group will meet in the Damon room. So you may, if you don't know where it is, please ask, and we'll let you know. Yeah, I think. Thank you again, and see you all tomorrow. Unless any of you want to have a last word. No. Okay. Thank you.
Please take cake and chips home.
Thanks. That was great.
I feel you were cakes.
Yeah, I'm also feeling